Hey everyone, it's Dr. Walker. Let's look at an example from video 84C on the physical pendulum. In this example, we have a uniform rod of mass m and length L is pivoted about one end and oscillates in a vertical plane. So here's our pivot over here, and we have this rod oscillating. So this is a physical pendulum, since the mass cannot be approximated as a point mass. The size and shape of the object matters. First, we want to find the period of oscillation if the amplitude of the motion is small. Now, this fact here, right, this just means that we can use the equations that we found in our video where we use that small angle approximation. So we can use our equation for period. The period equals 2 pi times the square root of I over mgd. If we had large oscillations, we wouldn't be able to use this equation. We just need to plug in all of our givens. What is the moment of inertia of a rod when it's pivoted about one end? You may remember, or you may look in your equation sheet, but it's 1/3 ml squared. And then the mass is m, and then g. And then what's going to be the distance d between the pivot point and the center of mass? That's d. Well, the center of mass is halfway, so the distance d is going to be L over 2. So this is an exercise, just plug and chug kind of thing. Just go ahead and simplify. Cross out one of the L's here. And we're going to end up with, we can flip both of these fractions, we can cross out the m. We're going to get 2L over 3g. We can flip both fractions. So that is the answer for part A. Let's look at part B. It says now, suppose the pivot is moved to a distance L over 4 from the upper end. So now the pivot's not here anymore, the pivot is right here. What's the period this time? So the process is going to be very similar. It's just now we have a different moment of inertia. Do you remember how to find a moment of inertia when you switch that pivot? That's right, you got to use the parallel axis theorem. So let's find the moment of inertia. I equals I center of mass plus md squared. The moment of inertia about the center of mass is not the 1/3 ml squared, right? That's about one end. When you pivot about the center of mass, the moment of inertia is 1/12 ml squared. Plus m, and then what is our distance? Our distance from our pivot to our center of mass is just going to be L over 4. So L over 4, make sure to square that whole thing. So when you do 1 over 12 and then 1 over 16, find a common denominator, you're going to get 7 over 48 ml squared. Now we're ready to plug and chug to find our period. Our period is equal to 2 pi times the square root of I over mgd. So the I'll just go ahead and write down I over mgd just like before. So let's write it one more time. 2 pi square root of the I, which is this one, 7 over 48 ml squared, divided by the mass times g. And what is our distance from the pivot to our center of mass? It is L over 4. So now we go ahead and simplify. We cancel out an L, and then we're going to flip our fractions, cancel out the m. We're going to end up with 2 pi times square root of 7L over 12g. And I only flipped the bottom fraction here. I just kept 7 here and 48 here. Alright, so that is our answer. This was an exercise in using the equation and going back to a few lectures ago where we had to use the parallel axis theorem.